All right, before we get back to the neural network stuff, Lab 2 is finally ready. I will also open the Canvas submission site for this as well after the class. Lab 2, so I'd like to spend a little bit of time going into the what exactly it is and what you're supposed to do in it and things like that, because I don't think it'll be a very friendly lab if I just gave you a blank piece of code, like hardware piece of code, and asked you to do something, because we really didn't have time to go into too much detail about, actually how to do things. So this guy is supposed to guide you through at least the basics of what I think should be done for the purpose of Lab 2. I will upload this video as well as the set of slides, and hopefully this will be enough for everyone to do Lab 2 without too much pain. All right. Lab 2 is the contents of Lab 2. The goal of Lab 2 is pretty much the same as the goal of Lab 1, in that we are trying to implement a fast version, or at least in the case of Lab 2, we want to implement a power efficient version of the fully connected layers in a neural network. And we will do that for the purpose, in the context of Lab 2, we will do that on an FPGA to get high performance and high power efficiency, well, at least to give an example of how we can get high performance and high power efficiency on a hardware implementation. And we're going to do that on a open source piece of hardware, on an open source toolchain, software toolchain, et cetera, et cetera. That's why it took a little bit of time for me to get all the code set up. All right, to set up the development environment for Lab 2, you will have to install the virtual machine, the VirtualBox virtual machine with Yosis and BlueSpec installed on it, according to the PDF file that is currently uploaded on the course website. Let me see if I can actually, the course website. This PDF file is very, very simple. It's just a couple of screenshots guiding you through how you can actually install the VM, import the VM, and connect to it over SSH. And once you set up the VM, it will have all the tools, open source tools pre-installed on it, including the BlueSpec compiler and the Yosis toolchain, which is an open source toolchain for compiling Verilog code into the FPGA, into this particular FPGA at least. And since the BlueSpec compiler is open source, which translates BlueSpec to Verilog, and the Yosis toolchain is also open source, which compiles the Verilog files to this particular FPGA, we can have a completely open source toolchain from getting from BlueSpec code to actual hardware. And once you have the VM installed, you start the VirtualBox VM and then clone this Git repository. I think it should also have a shell script in there that says clone project or something, which actually clones this Git repository automatically. But if it doesn't, this is the URL. And all the files for Lab 2 will be located in the repository that is cloned, inside projects, inside neural network fully connected layer. And kind of as an aside, this is the board that we will be targeting for the purpose of Lab 2. Although you don't have to have this board or anything. It's just that the toolchain is configured to generate hardware targeted for this particular FPGA board with this particular FPGA chip. It's a board called ULX3S. This is where the name comes in. This particular board uses a Lattice ECP5 FPGA, which is, I think at this point, the largest FPGA, the most capable FPGA that has been completely, well, almost completely backwards, almost completely reverse engineered, so that open source tool chains can generate bit files for it. So it has open source support. The big thing about the ECP5 FPGA, which is the chip you see here, the big thing about the ECP5 FPGA is that it advertises very, very low power, less than 1 watt of active power consumption. And it's also a very small size. As you can see, the SD card slot being here as a size of reference size. This is the HDMI port. You can kind of get a sense for how small this board is. So it's very small in terms of physical size, but also in terms of capacity, it also has a very small size, about 85,000 programmable units, which is as opposed to something like you would find on an Amazon F1 cloud instance FPGA, which could go up to like 1 million. So this chip is very low power, kind of small, kind of slow, but it's a pretty good fit for IoT devices or some hardware prototyping projects. So it's a pretty popular, one of the more popular chips for at least on the open source toolchain. So that's why we're targeting it for Lab 2. And once you clone the project, you can cd to projects NNFC. And then if you type make bsim, it will do a bunch of things, which will build the BlueSim version of your code, which is a functional simulator. It creates a binary file, software binary file, which when you execute, it will behave as if at least it behaves in a cycle by cycle accurate way for how the resulting hardware will behave when you actually synthesize it to hardware. But bear in mind that because it is a simulation, and you can actually run the simulation by typing make run sim. And inside the make file, runsim actually has a dependency on make bsim. So if you don't necessarily have to type make bsim all the time. If you want to run the simulation right away, you can type make runsim and it'll make it and then run it. One thing to bear in mind is that the simulator, because it is a simulator, it uses software to actually simulate what would exactly happen cycle by cycle inside the resulting hardware. So the wall clock time that it takes for the software simulator to execute, so how long your simulation runs, has absolutely nothing to do with how fast your resulting hardware is. So that's one thing you have to keep in mind. When you measure performance, you actually have to count cycles inside the hardware code. And that's really the only way you will know how fast your design is. How long it takes when you run the simulation, and it has absolutely no relation to how fast your actual hardware is. Anyways, if you type make runsim, it builds and runs the simulated model of the accelerator. And if you type runsim, you will see this output. You type make runsim. I typed it inside Vim, and then it runs the simulator. And then it prints out some messages from the simulation. And on the software side, after the computation is done, it compares the results. It doesn't complain about errors, so it seems to be okay. So what does this output mean exactly? So it's saying that it emitted, at least in this example, it emitted 256 elements 8 times. So 2048 element output. Each element takes about, it takes 3 million cycles or so to emit a total of 256 elements. So per 256 elements, about 3 million cycles. So dividing it by 256, it's about 12,000 cycles per emitted element. And calculation results are close enough. And the question here is 12,000 cycles per emitted element, is it good, or can you make it better? And before we actually get into this analysis, I guess I first need to give a little bit more detail about what the actual computation it's doing is and how the computation is organized to run it. So if you look at the clone directory, the project directory NNFC, this should be lowercase. It includes many files, of a lot of it for make file support, a lot of it for code wrangling, all that stuff. But that's just baseline stuff I built for the purpose of Lab 2. But for the purpose of Lab 2, the only 2 pieces of files that we are interested in is these 2 things: nnfc.bsv, which is a BlueSpec file, and the CPP subdirectory, there's nnfc.cpp. So the first one is a BlueSpec file implementing the accelerator. And the second one is a CPP file communicating with the accelerator. So this is the host side, and this is the accelerator side. These 2 pieces of files will be the only thing that you need to edit. It will be the only things you actually need to submit. And what these two files do is pretty much, the same thing we did for lab 1. It's at the bottom of it all is just matrix multiplication. So what it does is that it takes an input matrix, which will be initialized in software. The weight matrix will also be initialized in software, and the output matrix, which will be calculated inside the hardware by multiplying these two matrices together. The size of the input matrix is first has a height, so row number of input count, and the column size of input dim. So it's a matrix. It's not a square matrix. It can be a square matrix if you set the parameters right. It doesn't have to be a square matrix. It is a matrix of height input count and width input dim. And because we are multiplying the input matrix against the weight matrix, because this row has to be multiplied against this column, and then this column, and then this column, and then this column, so on and so on, to generate this value, this value, this value, this value. As we are used to this from the matrix multiplication, high school level matrix multiplication stuff. So the width and the height are the width of the input matrix. Input dim is the same as the height of the weight matrix, which should also be input dim. And the width of the weight matrix is output dim, because the width of the weight matrix represents how many columns will be in the output matrix. So this is the same, output dim and output dim. And basically what the application does is multiply these two input and weight matrices to generate the output matrix. That's it. Right, and because there are input count rows in the input matrix, there will also be input count rows in the output matrix. So if we have an input 0 here, which would represent, if this was part of an image recognition neural network, this input 0 will represent some intermediate values, intermediate model output of a particular input image. So this will represent some data in input 0, image 0, image 1, image 2, image 3, so on and so on. For input 0, it will generate output 0. These two things will correspond to each other. Right now this is wrong. Right now in the code, input count is 64. Wait, no, this is not wrong. It is actually 64. Sorry, I changed these numbers. I was changing these numbers yesterday and got confused. Yeah, anyways, if in doubt, look at if these are defined in main.cpp/main.cpp. So when in doubt, you can actually look at this file. Just because it will be a kind of a hassle, at least in the context of this lab, to try to make all this variable. So for the purpose of, in the context of this lab, assume that input count is a fixed value, input dim is a fixed value, output dim is also a fixed value. Yeah, if you have to make assumptions about the matrix sizes, just make assumptions. I'm not going to change these numbers for when I'm actually evaluating your submissions. Yeah, so in context of the application, what we're doing is that what we're doing is per kernel invocation, so to speak. We are processing batches of 64 input images. And each input image at this point in the neural network evaluation has 1,024 features. So the previous layer in the neural network had 1,024 outputs. And this layer of the neural network will have 64, if it is 64 outputs. So a vector of 64 output will be sent either to the next layer in the neural network or to the output. Yeah, and assume these values are fixed for lab 2, just because it makes our life simpler. And the accelerator architecture inside the hardware looks a little bit like this. This might look a little bit daunting, but I'll go through all of this. So the accelerator has 2 input ports and 1 output port. If you look at nnfc.psv and then look at the implementation module, make nnfc, it will have an interface that defines these 3 ports. So there will be 2 input ports, action method wait in, which the outside world uses to send in wait values one after another. And we'll also have a method action data in, which the outside world, in this case, it will be the host software, which sends in the input data from the previous layer one by one into these 2 action methods. And once the internal computation is done, the outside world can extract the results of the computation from an action value method called result get, this way out, and this goes to the host software. And if this is a little bit reminiscent of the output stationary, the wait stationary, all these methods of doing parallelizing neural network computation. But in this implementation that we have right now, the input from the host is broadcast to all PEs in the architecture. Kind of like what we talked about in the previous lecture. So for every single data in that comes in, it is replicated 8 times because initially in the code there are 8 PEs. It is replicated 8 times, so the input is replicated 8 times and broadcast to all the PEs. And once the computation is done, it is all gathered. Whenever output data is available, it just collects all of them and serializes it, sends it out one by one. If there's 8 pieces of output, it sends it one by one over 8 cycles. And the weights are also sent to all the PEs, but because of the computation characteristics of the computation, the weights are not broadcast, because if the input is broadcast and the weights are also broadcast, all the PEs will be just doing the same piece of computation always. So the weight is sent out round robin. The first weight is sent to the PE0, the next one is sent to PE1, the next one is sent to PE2, so on and so on. What this looks like in terms of computation is a little bit like this. If you look at the weight matrix, so let's see, because the height is the input dim and the width is the output dim, as the weights come in from the outside world, the very first element weight value will be sent to the PE0, the next one will be sent to PE1, the next one will be sent to PE2, etc., etc. So all of these PEs will be responsible for generating subsequent consecutive slots in the output vector. So for input 0, we want to generate output 0. PE0 will generate 1 element of it, PE1 will generate 1 element of it, PE2 will generate 1 element of it, and if output is larger than 8, then PE0 will generate one of the other, another column, so on, so on, and so on. So the point is, any column will be assigned to a single PE in a round robin fashion. So as we go on, this column of the weight matrix, for example, will be entirely sent to PE0 eventually. Although we don't send it in this direction, we send it in this direction. We scatter it across all the PEs, but eventually, when it loops back to the next row, this will be sent to PE0, this will be sent to PE0, this will be sent to PE0, etc., etc. Hopefully, this is fairly straightforward. And I'd like to put a disclaimer here that this design favors ease of understanding rather than performance. There are better ways to actually implement this for higher performance. Maybe some of you would like to explore that in the code. But right now, as it stands now, the code is optimized a little bit more for understanding than performance, pretty much. And what that looks, if you go a little bit more detail into the organization of the computation, it looks a little bit like this. For each row of the input, let me see if for each row of the input matrix, they have to be multiplied against columns of the weight matrix. And because columns of a weight matrix are assigned to PE0, PE1, PE2, so on and so on in a looping fashion, the output, in a looping fashion. So for 8 PEs, 8 columns are sent to completion first. So say in this simple example, because now at this point it only shows 3 PEs. Let's say we have 3 PEs. Then in that case, the software, the weight stored in the SD card is loaded such that we send 3 columns first, and then 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 3 columns first, so on and so on, until the entirety of the 3 columns are sent out. If there's 8 PEs, entirety of the 8 column is sent out first. And once all of this is done, we start sending out the next batch. So that's how, when the computation is being actually done, for each input matrix row, the input matrix will be sent by because this is output dim. The rows of the input matrix will be sent out if there's 8 PEs, out dim divided by PE count times, because there will be 1, 2, 3, 4, let's say 3 chunks of the input matrix will be sent out 4 times. And if you look at the software code, which actually sends these files, it will become pretty straightforward. But I'll get into details about that in a bit. Right. So, and for every column batch, it generates a vector, subvector of the output matrix. Yeah. And inside each PE, and it's a simplified view of what this PE actually does. You will have to look at the code to understand it better. But for the purpose of Lab 2, I don't think you will have, I mean, depends on what you want to do, but hopefully you won't have to actually look at and understand all of this, because it's a little bit too much to ask for a couple of weeks. But anyways, the PE implementation is inside make mac PE in the same file in nfc.psv. This thing also has 3 ports, 2 input ports, put input and put wait, and one output port, result get. Put input comes straight from the software, so it sends in a vector of 2 values, a tuple of 2 values. The floating point value for the input inside a single cell in the input matrix, and the 8-bit index, input index, which basically says which input does this belong to. So if we have 64 input values coming in, so 64 images, this input index will represent which image it is. The weight is just a float value. There's no index tied to it. So which location this weight comes from really depends on how the weight file is laid out in memory. And we'll get into that in a bit as well. And for all the input that comes in, what basically happens is that the input index gets pushed into what is called the partial sum index queue. So which XY location in the resulting matrix is this resulting multiply accumulator supposed to go to eventually? So input index, output index, and the row of the weight matrix. So basically, this is, if you think of the triple for loop implementation of matrix multiplication, this would be I, this would be J, this would be K. This will become more obvious as we look at the actual hardware code. But right now, this is like setting the background for all of this. And for the 2 float values, you put it into the multiplier, and the resulting value of the multiplier gets pushed into the adder, and it gets added together with the current partial sum, because that's what the matrix multiplication thing is supposed to do. And based on the K value, which goes from 0 to 1024 in our example, because the input dim is 1024 in size, fixed for this purpose. So if the row is 1024, we know that this partial sum is now the full sum of this row. So we finished calculating a single cell in the output matrix, so that gets pushed down into results. If it's not, if the column is not done, if you're still at the index 123, or for example, the partial sum gets pushed into the partial sum queue so that it can be added again to the next tuple that comes in. And yeah, the output will take the input index, the output index, and also the added result, so that when this gets relayed to the software, it can pretty much basically be just written to input index by output index and some value. The software side of things is very simple. An interesting question here is that in this current implementation, do you notice a performance issue? There is a performance issue. Right now, only one column can be processed at a time, because the adder requires a value that comes in from here, requires a value that comes in from here. So if we are processing partial sum implementations, we have to wait until the add results are done. The previous add results has to be finished before the results of which can be available for the next add operation. And because this add operation has a multiple cycles of latency, this is completely not pipeline. And we'll get into the details of this again in a bit. But right now, the point is, even though the multiplier operator and the add operator are all fully pipeline implementations, although even if it has multiple cycles of latency, you can always inject one request per cycle. That's actually not how it's being used. At cycle 0, you push in, let's say you push in something to the adder. At cycle, let's say 6, the results come out. But while the results come out and then gets pushed back into the results, can be pushed back into the results again, over those 6 cycles, no new requests can be pushed into the adder, which underutilizes the implementation, underutilizes the circuit. So with this knowledge in mind, let's look at the performance again. Remember that we were taking about 12,000 cycles per 1,024 elements in a column. So each of these elements, each one of these 255 elements is an element that needs to be written to the resulting matrix, which means each of these elements represents 1,024 multiply accumulator operations, because that's the input dimensions. So 12,000 cycles per 1,024 elements in a column, which represents about 12 plus cycles per multiply accumulator operation. This is not pipelined at all. We want this to go to 1/8-ish, because we have 8 PEs. Assuming everything is pipelined and we have 8 PEs, we will be getting a one result out every. We want a multiply accumulator operator to take on average 1/8 cycles, because it'll be parallelized over 8 PEs. And yeah, that's what we want. But right now it's nowhere near 1/8. It's 12 plus cycles per map. That's bad. The sum of the latency of the mult and add operators is about this much, which means there's absolutely no parallelism across PEs. And there's no pipelining. So that's bad. This is something that we need to improve. And I'm going to just walk you through how it's done, at least a significant part of the way. So let's get on that. So how do we solve this? I could ask you to just toss the code to you and ask you to figure it out, but I don't think that would be a good thing to do given the time constraints we have in the quarter. So here's a significant direction towards the solution. We need to either work on multiple rows or multiple columns at the same time, or both. That's the solution we can have to actually solving this problem, because we need to be working on multiple independent pieces of work to have multiple independent multiply accumulator operations injected into the map pipeline at once, so that it doesn't have dependencies across requests, so that we can have independent operations all in-queued into the pipeline. And also across different PEs as well. So I said we need to either work on multiple rows at once or multiple columns at once. So if working on multiple rows at once in the output matrix, because this is input dim, working on multiple rows at once represents working on multiple input rows processed at once. So we process not only this row, and then we don't wait until this row is completely finished before moving on to this one. We work on batches of how many rows at once, and then batches of how many rows at once. That's one way we could do it. Or we could work on multiple columns at once, where multiple wait columns are processed at once. Multiple wait columns being processed at once would be, we chop this column-wise of the output matrix into multiple chunks. So which one do we start with? I mean, spoilers is that eventually we would need to get both to get the 1/8 cycle count of peak performance. But which one is the more urgent one? Because right now I will tell you that if we choose the wrong one, when we implement only one of these approaches, it's not going to have any impact on the performance right away, because the other one is such a large bottleneck. And again, I could ask you to figure this out, but that would be not good. So the answer to this question is that the SDRAM, which holds the weight values on board, is slow on our embedded platform. This is just a characteristic of the board that I chose to use. If you look at source SDRAM.bsv, it has the controller implementation for the SDRAM. You can take a look at it if you're interested. But the bottom line is that for every single 16 bits that is read from the SDRAM, due to the characteristics of the chip, it takes about 5+ cycles to read 16 bits. It has some dynamic characteristics as well. If a bank is open or previously opened or not opened, if the row has been read or not read, et cetera, we'll talk about memory in a bit in the later part of the course. But the bottom line is that to read one float weight value from the off-chip DRAM, it takes about 10+ cycles. And this continues the trend from when you were talking about CPUs to GPUs to FPGAs to ASICs. If you have to go off-chip to get memory, it's slow. That's just how it is. And if counting also the request and response rules, how that takes, et cetera, about 12+ cycles per computation sounds about right, because it will take 12+ cycles to read. Remember, 12+ cycles came from dividing from the calculating the performance numbers from the naive implementation. And yeah, 12 cycles per computation sounds about right. If every single, because the weights values that are read are not being replicated, if they are being, if every single piece of computation, if every single map operation needs a new weight value to be read from the SDRAM, it is natural that every single computation will take 12+ cycles to complete. So this sounds about right. So SDRAM is where the weights are stored. So it is not, the bandwidth of the SDRAM in light of the 5+ cycles is not feasible to load and work on multiple weights at once. So we have to go the other way around. We have to start working on multiple inputs at once. So if you, from the previous slides, do we work on multiple rows at once? Do you work on multiple columns at once? We're going to work on multiple columns at once. So working on multiple columns will look like this. So we will load the input matrix in batches. And for each weight matrix column, P1 and onwards are not shown for simplicity, but they should also be doing the same in parallel. So for a batch of input matrix input, we should be multiplying each of these rows against a column of the weight matrix to generate each of these cells. Right. For each PE, each weight value needs to be applied n times for n parallel input rows. So if we have, say, 3 parallel input rows coming in, the weight matrix needs to be replicated, at least applied 3 times, one for this one for this one for this one. And that's the implementation that we're going to do for the beginning. Input order must also change. So input coming in from the software should also be changed. So the software needs to be modified to change the way the input data is stored, sent in. Instead of sending in one row first, one row next, and one row next, we send it 1, 2, 3, 1, 2, 3, 1, 2, 3, and so on and so on. So all of these have to be changed, and I'm going to walk you through all of that. So let's look at how we can do something like this in BlueStack. Say we process 8 rows at once. The previous example showed 3 rows at once, but let's say we process 8 rows at once. So this is inside NNFC. If you look at NNFC, somewhere in the code inside the Mac PE, inside the Make PE implementation, you will see this. This is wait in queue is where the waits come in from the outside world. And this is just a rule that relays it to the waits queue, which the PE will use to actually do something. And because we want to process 8 rows at once, each of the columns of which are coming in an interleaved fashion. So all we have to do is replicate this every single wait value 8 times. So we add a register for holding the wait value to be replicated and a counter register to count how many times we want to replicate this. So when in the beginning of the world, when the wait replicate count is 0, we take in a new input from the wait in queue, and then we relay it to the wait out, the actual wait queue. And then we store in the temporary register, we store number 7 inside the wait replicate count because we want to replicate this 8 times. We sent out 1 already, so we have to send it out 7 more times. And when wait replicate count is not 0, it goes in here. We just count down the wait replicate count and then just enqueue the same value 7 more times. So this is how we're going to replicate the wait value 8 times inside each PE. So that happens. And inside a separate rule called enqueueMac, you will find it inside the same file. Remember, there was a partial sum index queue, which needs these 3 values: input index, output index, and row, to keep track of which location in the computation we're doing, so I, j, and k values. And here's a FIFO called partial sum index queue, which includes 3 tuples: input index, output index, and the row, called curmac IDX in this code. So input index is given with the input from the software. Row is increased 1 per every MAC operation, because that's natural. We move forward with each MAC operation. And output index is increased by PE ways, which is PE count, every time the row exceeds, so this row value exceeds the size of the input. Because if you're multiplying each column, every time we reach the end of so this is a weights matrix. Every time you reach the end of the size of the input dim, we move on to the next column, which increases the output index by 1. And because we have 8 PEs, instead of increasing it by 1, we increase it by 8, because that's where the next assignment is. So right now, that's what's happening here. And curmac IDX is the row count is being increased by 1 per every MAC operation. And if Mac IDX reaches the end of the here it is. If the Mac IDX reaches the end of the input dim, we increase the out IDX by PE ways. And if the next IDX also exceeds the size of the output dimensions, we move to the next row. Otherwise, the MAC index is just increased by 1. So that's what it was doing originally when we were just processing 1 rows at a time. But now, if you want to process 8 rows at a time, process 8 rows at a time, the curmac IDX, so the row count, because we're processing 1, 2, 3, 4, and then 8, 1, 2, 3, 4, 8. One after another at once. So this current row count only increases after 8 operations. So we divide. So when we push things into the partial sum index, we divide the curmac IDX by 8. by shifting it down 3 times. And let's see if I have any more comments. Right. And also the way we count whether this, chunk of 8 values has reached the end of the input dimensions is done by also dividing it by 8 to make sure that instead of doing checking if we performed 1024 pieces of multiplier accumulators to determine whether we reached the end, now we have to check if we did 8 times 1024 operations, so this much, to check if we reach the end of the column batches. So yes, multiple inputs for the same output index. So the same output index now arrive as a burst, one after another. So the row must increase every 8 max, which is what's happening here. And the output index also increases by every 8 max. This is what's happening here. So fairly simple enough change. And to keep, accommodating for the change of 8 rows arriving at once. And thing that we haven't talked about very much is at the beginning of each column, at the beginning of, again, looking at the weight matrix, at the beginning of each processing column, we have to enqueue 0 to the add module because we have to give it an initial partial sum. So we start from an input value of 0, the partial sum value of 0, pretty much. So originally, this is what the code looked like for that. If the Kermac index is 0, which means when we first started the next column, we input 0. And if not, we take the output from the partial sum Q and then add that to 0, add that to the add, push that into the add operator. But now, because we are processing multiple rows at once, multiple columns at once. When we had this implementation, this original implementation, we only enqueued one request into the pipeline at the beginning. And this pretty much results in a non-pipeline because every time we have to wait for this code to be invoked, we have to have the previous results ready. So there's only one request in the pipeline at any given time. But now we can have more requests in the pipeline since we have multiple independent rows are being processed at once. So say we replicated 8 times, so we, instead of checking if the Kermac index is 0, we check if it's smaller than 8 because we want to have up to 8 operations in the pipeline at once. So for 8 of these things, we push 0 into the add forward queue and nothing else is changing. That's it. And the software, like I mentioned before, the software needs to be modified a little bit to accommodate for all of this as well. So the hardware now assumes 8 input rows will arrive interleaved. So instead of sending this row at once, this row at once, and then this row at once, we are sending it this column first, and then this column, and then this column, and then this column, and this column until we send everything. So before the software version, the software part of sending the input was non-batched. It was sending one image to completion and then one image to completion. So I is looping over images, and J is looping over the columns. It is divided by the number of PEs because each row, if you were multiplying the input row against the input matrix against the weight matrix, this one row will have to be sent, let's say the output dim is 64, this row would have to be sent 64 times to generate the output row. But because we have 8 PEs, at least right now, and 8 PEs are working in parallel, we only have to send it to, this row is being replicated automatically across 8 PEs. So we don't have to send it actually 64 times. We only send it 64 divided by 8 times. So this is what's happening here. And for each row, we were sending just the entirety of the input DIN. So this row. But instead of that, we're now going to send 8 row chunks, and then 8 row chunks, and then 8 row chunks in an interleaved fashion. So this is going to change from simply looping over the input count to input count divided by parallel rows, and the parallel rows is 8 in this example. This doesn't change. This doesn't change. But we add another for loop inside, which sends data in an interleaved fashion. So this is basically what's happening. KK is looping through parallel rows. So this, so on. And the indexing changed, and the parameters we sent to the accelerator also changed to tell it which input row this particular value comes from. And that's it. This is the only changes you need to make to actually perform batched row processing inside the accelerator. And now we can actually look at the performance. So this was on the left, you see the performance that we were seeing from before, the naive implementation, 3 million cycles per 256 elements. But with the batched processing, the numbers decreased significantly, only, quote unquote, only 400K cycles. So almost an order of magnitude, about 8 times actually, performance improvement over the naive implementation. So if you do the math, before it was 12 plus cycles per computation, but now it's 1.53 cycles per computation by replicating it 8 times. I mean, processing 8 rows in a batch. And this is much better than 12 plus, but still not quite 1/8 cycles yet, which would be 0.125 cycles. And we're not quite there. But, oh yeah, before we do the but. And right now we only know the cycle count for performance, but what about wall clock time? If you want to know about the wall clock time, the actual, the real world time performance, you can do, instead of typing make bsim, you can try making make pipe t build.log command. Bear in mind, before you actually do this, you have to build some tool stuff. Inside the ULX 3S directory, I think there's a tools directory where you have to go inside and do make. There are some support binaries you have to do, but inside the Git repository, there should be a piece of text that describes how to do this. If you look at the readme.md. Anyways, when you run the make file, it will take a few minutes. It creates build.log and then build.hardware.bit, among a bunch of other files. Hardware.bit is the file that is actually programmed to the FPGA. This is the bit file, which is sent to the FPGA to configure it. And the build.log is what gives you some information about the resulting circuit. And the build.log consists of thousands and thousands of lines, hundreds of thousands of lines. But if you look for the message device utilization, it'll tell you information including how much CLBs this design took. So our 8-way implementation apparently takes about 47% of the chip. It also tells you how many multipliers it used. It only used 8 out of 158 available, but we only have 8 PE, so that's what's happening. So you can kind of see that this, like I mentioned before, it's not a particularly performance optimized way of doing things, because if it was a really performance optimized way of doing things, we would have used almost all of this 156 multipliers to actually do useful computation, but we're not doing that. So anyways, so that's what's happening. And also 7% of the on-chip memory. And if you look for max frequency, it tells you the maximum clock frequency of the circuit that you design. So in this design, you're using 2 different clocks. So what is called 2 different clock domains, the 25 megahertz clock and the 100 megahertz clock. The name is not important. It's basically saying the design actually cannot hit 100 megahertz, but for our purposes, that's fine. it is telling us that our implementation can reach 62 megahertz. So using the cycle count coupled with the megahertz count, you can know how much in terms of actually wall clock seconds, how long the operations will take. And right now, just ignore the 25 megahertz clock because it's just used for interfaces. So what caused this timing issue? We didn't reach 100 megahertz, we only reached 62 megahertz. And why? What's the critical path that caused this? Is you can find this out if you look for the critical path report for this particular clock. There's a critical path report generated for each of the clocks. So there's a bunch, but what we're interested in now is the 100 megahertz clock, this one. And I just cropped it here. There's a lot more text below, but if you kind of eyeball the code, you can kind of know that the critical path starts from the partial sum index Q to something. It's a combinational path that starts from the partial sum index Q and ends at somewhere else, which I omitted from the line. And this is an important piece of information if you want to keep optimizing this. But anyways, so that's the guideline for, walkthrough for what exactly needs to be done for the purpose of Lab 2. I'll upload the slides, I'll upload the video as well. So hopefully the actual code writing part doesn't cause too much grievance. So for the purpose of Lab 2, what to do is pretty much just apply the changes that is introduced above and measure the performance in terms of cycles. It should be the same as what I talked about in the what I presented in the slides. The actual creative part of Lab 2 is look at the code, try changing some parameters to evaluate, can this approach go further with larger number of parallel rows? Is 8 the limit? Is 64 the limit? Is there a limit? If you keep increasing this value, if you keep increasing something else, will the performance just keep increasing or will it taper out somewhere? And if not, what do you think is the limiting factor? And a hint for this is look at source uart.psv. And there's a module called make uart vsim, which is the module that transports data from the host software to the FPGA. There's a hint for why we would reach, if there's a limit in terms of cycle count per operation for performance that you reached, there's a hint that the reason might be lying here. And also the third evaluation point, creative point, is what is limiting the clock speed in the design that you end up with. So what to submit when you're done is to submit 3 files. Your modified nnfc.bsv, your modified nnfc.cpp with your best effort implementation, which would be pretty much the answer to this one. If you can actually discover the limiting factor, and I don't think, if you actually discover the limiting factor, and if you actually figure out a way to fix it, that would be awesome. If you actually go beyond this approach and actually reach higher performance, I guess that would pretty much be an automatic A+. But yeah, but that's not an expected part. That's not an expectation for this lab anyways. And also the third file that you need to submit is a report file, either in text or PDF or whatever, with short answers to the 3 evaluation questions above. And that's it. It's due at the end of finals.